Alright, moving on to chapter 20.4 and on, we're talking about electric power and energy. Starts out by saying that power is associated with electricity. Okay, yeah, so what gives? We know that there's 25 watt bulbs and they're dimmer than 60 watt bulbs. So depending on the brightness of the bulb you want for your dorm or your bedroom or whatever, you get you might want to have a 120 watt bulb for your workshop or kitchen, but when you're reading you might want a 10 or 15 watt bulb by your bed to get a nice dim light. So there's your 25 watt bulb, there's your 60 watt bulb. Then you got to be a little bit careful when you're looking at LED bulbs or CFL bulbs like this. This is a CFL, a compact fluorescent, because they'll give you an equivalent wattage. So people are associated with a 60 watt bulb as being bright, but this is a 15 watt bulb. So the 60 watt bulb actually uses 60 watts of energy. The CFL bulb only uses 15 watts, but it outputs the equivalent amount of light as a 60 watt bulb. So you got to be careful with that stuff when you're buying them from the store. There's also an important thing here. In the US, it's 120 volts is what comes out of the wall in your house, and it's connected to or compared to 240 volts in Europe. So if you fly to the UK, for example, and go to plug your laptop into the wall, first of all, you're going to need an adapter, but second of all, you got to make sure that when you look closely at the label on your power supply, that it actually can be plugged into 240 volts without exploding or starting a fire. Okay, so what is power? Power is change in energy over time. Okay, so energy is Q times V over T, and what you notice here is Q over T meets our definition of current, charge over time. So we call power, we can calculate it using PIV, P equals IV. So I remember V equals IR as VER, and P equals IV is PIV, and that's the power coming out of a circuit. It's simply the product of current times voltage. Okay, SI unit for potential energy is the joule, and power has units of joules per second, which is a watt. 1 watt is a joule per second, but also 1 amp times a volt. So there's a lot of different units here floating around, but just remember your equations and you'll be fine. Okay, so a car, they used to be cigarette lighters in your car. Now they're 12 volt outlets, and they're hooked to a 20 volt battery, so they can output a maximum of 240 watts from your car battery, because they could push out as much as 20 amps at 12 volts. So you can plug a microwave or a grill into your car or something like that and cook your hot dogs, or your tofu hot dogs. Okay, anyway, sometimes we use kilowatts. All right, which is 1,000. Okay, so now we can combine P equals IV with V equals IR and substitute I in here, or V or R, whatever we want to do, and we get 3 equations. And these are really important equations. P equals IV, P equals V squared over R, or P equals I squared R. And this allows you to figure out the power in a circuit, either based on the current and voltage, or the voltage and the resistance, or the current and the resistance. But it allows you to get rid of either, there's no R in the top one, there's no I in this one, there's no V in this one. So depending on the problem, you can use one of these equations to solve. Okay, now that gets tricky here. Let's say I've got a battery, and we've got 1 resistor, 2 resistors like this, R1, R2, and battery 1, and the total current going around the circuit and coming back into it. You could calculate the total power in the circuit, the total voltage and resistance, or the total current. But you can also use the same 3 equations here for just one of the components. So we've got I, and we've got V1 and V2. So at this R1 resistor, it's going to have a different voltage. At R2, it's going to have a different voltage. Since they're in series, they're going to have the same current. But you can see that using V equals IR, we can have different P equals IV values, so you can measure the power off one resistor or the power off another resistor. So P equals IV. So yeah, let me just plug this in. P equals IV1, so that would be P1. P2 is equal to IV2, or you could have P1 is equal to V squared, V1 squared over R1, or P2 is equal to V2 squared over R2. So you can see how this gets pretty powerful. Anyway, let's move on. Blah, blah, blah. Anyway, I don't think we have to do this one. This is looking at that light bulb that we plugged in for whatever. The previous chapter, there was a tungsten light bulb in a car. You can calculate what that is again here. Okay, so the cost of electricity, the cost is power times time. Okay, so the total cost is usually in cents per kilowatt hour, and we measure power in kilowatts, and so the total energy used is going to be the power times the time. If a watt is a joule per second and we multiply it by seconds, then we get joules, and so that's where that comes from. In California, let's say it's about 12 cents per kilowatt hour or 13 cents per kilowatt hour, something like that, versus in Iowa it's about 2 or 3 cents per kilowatt hour. Much cheaper to power an electric car in Iowa than it is to own an electric car in California, because, to drive a gas car in California, you got to pay about $4 a gallon for gas, whereas in the electricity is about, let's say you get a Tesla and it has a 100 kilowatt hour battery, something like that, and you end up paying about $1.50 per gallon of gas when you factor in the total cost to charge your Tesla every night. Whereas in Iowa, it'd be 10 times cheaper, 15 cents a night to charge it, or 15 cents a gallon. Okay, so in energy cost. But let's say you want to figure out the cost to run a 60-watt light bulb over 1,000 hours, which is about the lifetime of a bulb before it burns out. So, the energy that you're going to use is the power, the rate of energy usage times the total time. So you're going to run this 60-watt battery for 1,000 hours. You get 60,000 watt-hours. The energy is 60 kilowatt hours. Now the electricity cost is 60 kilowatt hours times 12 cents per kilowatt hour, gives you a total amount of money, about $7.20. So if you run this for 5 hours a day, it's a little over half a year of having a light bulb. Okay, so it costs about $7. Now for B, we have a CFL, a compact fluorescent bulb, which only uses 15 watts. So that means it's going to cost a quarter of the amount of money, so $1.80 to run that. It'll also last 10 times longer, so you're going to be paying $1.80 per 1,000 hours. And if you want 10,000 hours, then it's going to be 10 times the cost, so it'll cost you about $11 versus the 60-watter. You're going to have to buy 10 of those bulbs, and now you're looking at, a bunch of money just to run the thing, and then you got to pay more for each year and blah, blah, blah. So it makes sense to swap out your bulbs with CFLs when they burn out. All right, and then when you move, okay, this is what I did when I was a freshman in college. No, not freshman, a junior in college. Might have been a grad student. No, I think I was a senior in college. I moved into an apartment. I bought compact fluorescent bulbs, and I put them everywhere, but I kept the incandescents that were there when I moved in, and then this is really embarrassing, and then I took the CFLs back out and I kept them. So then when I moved, I didn't have to rebuy CFL bulbs because they were a little expensive, and then I put the incandescents back in. So, okay, I'm not much of a miser otherwise, but that's an example of something weird I did. Okay, 20.5, AC versus DC. So you may have heard of the band EC versus DC. Well, now you're going to learn where that comes from. There is a big debate about whether to use AC or DC to power everything. So AC current is alternating current, and DC current is direct current. So let's say you're trying to get energy from point A to point B. Well, there's a way to do it called direct current, where you just push the energy from point A to point B. And the other way to do it is alternating current, where you push and then pull and then push and then pull and then push and then pull. So the electrons wiggle back and forth rather than get pushed across the whole thing. Okay, so that's a big difference in the way to put your energy. And this is why we need transformers. When you plug a wall wart into the wall, you got to transform AC to DC, because all of your phones, all of your laptops, all your iPads and everything they all need to be powered by direct current. So here's an example of the difference between them. Voltage and current. Your voltage is 0 to t. Over that time period, the current is constant and the voltage is constant. That's DC. Whereas AC is not constant. It cycles between plus V and minus V, plus V and minus V, plus I and minus I. So that's a sine wave. That's a sine function, and it does that forever. Okay, so it's alternating between high and low and high and low and plus and minus and plus and minus. Okay, and this is the equation that measures the voltage as a function of time. The voltage at any given point is the initial voltage times the sine, which depends on the frequency of the lights that are, or the energy, how quickly the generators are oscillating, and then time is at any point t. So let's say you want to say, let's say it's 1 minute, 2 minute, 3 minute, 4 minute, 5 minutes, 6 minutes, 7, 8 minutes. You say, well, after 5 minutes, 1, 2, 3, 4, 5. After 5 minutes, what's my amplitude? Well, there's a V0 there. So that's my amplitude. So you can measure the total the voltage at any point using this equation. Let's see. The current, same thing. It oscillates as a function of your sine as well. And then you've got V equals IR at any time too. And yeah, 20.16b, that's up here, yeah. Okay, so if the current and voltage reaches a maximum at the same time, and minimum and minimum and maximum and maximum, then they're said to be in phase. Okay, so the thing you have to worry about sometimes is there's a flickering that happens with light bulbs. You can't see it with your eyes, but if you take a video of a fluorescent light bulb, they're actually not on all the time. They're flickering. And I don't know if there's a better explanation of it here. Anyway, so, and it's because they're oscillating with a at a certain rate, 120 times a second. Okay. All right. Yeah, and then so your power here, if it's IV, your power is IV, and I is sine of 2 pi ft, I0, and so on. So you end up with I0 V0 times sine squared of 2 pi. And when you do that, here's your power. If you have sine squared, okay, let's remember the sine function goes between 0, well, minus 1 and plus 1. Both sine and cosine oscillate between a maximum of plus 1 and minus 1. Okay. Okay, and depending on where you start, you use either sine or cosine. When you take sine squared, you no longer have negative values. It no longer goes from minus 1 to plus 1. It goes from 0 up to your maximum. So your power now is a positive value always, which makes sense because even when you're using negative current, you're still generating power. So just keep that in mind. We've got something called RMS current and RMS voltage, which is just I0 over the square root of 2 or V0 over the square root of 2. Yeah, you can calculate your average power using the same type of thing. RMS values are only used for AC, so Ohm's law for AC is IRMS equals VRMS over R, and you plug all that in for P and stuff. So if you're trying to do Ohm's law with AC currents, then you want to do that. Blah, blah, blah. Got an example here. I'll work through that. So here you go. Why to use AC for power distribution? You may remember Nikola Tesla was a guy a long time ago, and he worked for Thomas Edison. And, Nikola Tesla famously advocated for DC power transmission, but Thomas Edison pushed AC, and AC is what we all have. And AC is a little bit easier to deal with, and it's a little bit easier and more efficient to transmit over very long distances. But DC is safer, better, easier. So when it gets into your home, it's better to have little transformers that change it back into DC. Okay, bloody blah. Okay, that's pretty much it for the power stuff. So 20.6, we got electric hazards in the human body. So you got a thermal hazard, that's where it could burn you, electricity could burn you. You've got shock, which could mess with your heart. So when electricity passes through your body, it can change the rhythm, the current that's being used to beat your heart, that can mess with that. But as the current travels to your heart, it can burn all the cells in between. So there's two big problems with electricity: thermal burns and shock currents, which mess with your system. All right, so let's go through here. Go through this. So these are talking about protections and different things, like in the circuit breakers, like a fuse box, or most people have a circuit breaker in their with the bimetallic strip here in their houses, and only in old houses do you see these old fuses that you get a fuse box that you have to screw your fuses into the circuit. Okay, so the things that dictate whether a shock is harmful or not is the amount of current, where the current flows, how long you're being shocked for, the frequency of the current oscillation, which is 0 for DC. Okay, and also, it doesn't say in here, but you also need to worry about the voltage. So it's a combination of these things, as well as your resistance, your own voltage. You can see here, this is the symbol here. These little black lines are telling you that the person is grounded, which means when they touch the wire, the current is going to find a path and take that path out to the ground. So if you got nice rubber shoes on, you might be okay, or if you're wearing a metal cage, you might be okay too, because the current will not go through you. In the case of the cage, it'll go around you. In the case of in the case of rubber feet or something, there'll be no path for the current to flow, so it won't shock you. Okay, so here's some examples of effects. About a milliamp will give you a tingle. 5 milliamps is the max you can get before you have any, problems. 10 to 20 milliamps, you can get a muscle contraction. 50 milliamps, you can get some pain. 100 to 300 milliamps, you can get a pretty good shock and mess with your heart. And above that, you get starting to get burns, and at 6 amps, you basically die. Anyway, the thing with all these is, like it already said, you have to consider the amount, the duration, but you also have to consider the voltage, and if you have a bunch of current but a very, very low voltage, there's not enough potential to push the current through you. So it's really a combination of both. Let's see. So they try to go through some detail here so I definitely recommend reading that. Here's your frequency versus your current, and some other graphs here. Here's a cool thing showing you that it's like our Tesla coil. These wires are not connected, but they're arcing, and that's because they're close enough where the voltage potential between them is enough to cause the air to break down and become a conductor. Okay, so 20.7, nerve conduction. So the way nerves work and how your body communicates is by electrical signals. You've got your axons, your dendrites, and if you look at a regular, like a neuron, your neuron comes in, you've got the synapse between them, and the dendrites are reaching out and talking to them, and then your axon here is it's almost like an insulated wire, and you're trying to conduct signals down to the muscle and cause them to twitch. So these sheaths here are like insulators, and they try to get that signal as high as possible. When these sheaths break down, you have different disorders and make it harder for you to control your muscles, which is like, when your iPhone cable stops working. Okay, anyway, so there's some, if you're studying biology, this is a little bit interesting, just showing you how at the molecular level, it's Coulomb's law and the electrostatic forces that are really causing a lot of the things to be possible and how they work when we're talking about transmission of, different ions and things. Okay, blah, blah, blah. And yeah, so this is interesting, just talking about nerve impulses and just how it sort of works. So you've got the outside sodium, inside, and then just as it depolarizes and repolarizes and moves down your nerve. So that's pretty cool. Going down here, and here's your axon again. And continuing on, electrocardiograms. So it's ECG. The new Apple Watches can do this. You put your fingers on there, and what it's trying to do is measure the electrical currents. It's kind of amazing that it can do that. But I don't think I have to really talk about this too much. Okay, that's the end. Read this. It's pretty cool. It tells you about your heart. And that's the end of the chapter. Okay, talk to you later. Bye.